Hey everyone, so our goal for today is to find the acceleration, speed, and max height of objects in free fall. So when we talk about free fall, we don't necessarily mean an object just falling, we mean also going up, anything that's only under the influence of gravity. So we saw in some demonstrations and videos that all objects will hit the ground at the exact same time, regardless of mass. Okay, so regardless of mass. So we watched the video of the hammer and the feather on the moon. We watched the video of the bowling ball and the feathers in the vacuum chamber. So regardless of mass, all objects accelerate toward the Earth at the exact same rate, 9.8 meters per second squared. That value does change depending on different planets, but on Earth it's 9.8 meters per second squared. Okay, this means that the object's velocity changes by 9.8 meters per second every second. Okay, so the velocity changes by 9.8 meters per second each second. Right? So there was a quick little Mythbusters video here about a penny dropped off the Empire State Building. Actually, kind of left some of the work here accidentally. So if it's dropped off the Empire State Building, which is 381 meters tall, how fast would the penny be traveling by the time it reaches the ground? Neglect air resistance. So if an object is dropped, you know that the initial velocity is 0 meters per second. The final velocities are unknown. The acceleration of any object in free fall is 9.8 meters per second squared. And we know how far it fell. D equals 381 meters. All right, so using this equation here, Vf squared equals Vi squared plus 2AD, you can solve for the final velocity of 86.4 meters per second. Now, don't forget, obviously there would be air resistance in real life. Also, why did we use this equation? Because we're not given time. This is the timeless equation. So number 2 says, we call this number, just as kind of just referring back to the beginning, the 9.8, we call that number the acceleration due to gravity, which we abbreviate with a little g, and we call little g. This is a constant number near Earth's surface, which is equal to 9.8 meters per second squared. That is right off your reference table. Looking at this picture here, what do you notice about the value of g as you move away from Earth? Notice how g gets weaker as you move away from Earth, because there's less I guess the phrase is there's less gravity, or the gravity is weaker the farther you move from Earth. So farther from surface, little g goes down. All right, this should make sense to you because think about it. Like if you're all the way across the universe, you're really far from Earth, right? You are not accelerating toward the Earth's surface at 9.8 meters per second squared. Now in this class, g will always point downward. Always, always, always. And we're going to do some things with free fall problems we do in this class. First off, the initial, I shouldn't say velocity here, the initial direction of motion will always be positive. For example, if an object is thrown upward, up is positive. If an object is dropped, down is positive. Little g, which is the acceleration, will be positive if it helps the initial velocity, or negative if it hurts the initial. Now, a few people aren't really sure what do I mean by that by helps or hurts. Basically, what I'm saying is if it speeds up the initial velocity, it's going to be positive. If it slows down the initial velocity, it will be negative. We'll do some problems in a minute. So this question says a rock is dropped from a bridge. What happens to the magnitude of the acceleration and speed of the rock as it falls? So the acceleration remains constant. Okay, and the speed increases. Now, when we say magnitude, we mean like the size of the number. Don't worry about positive or negative. All right. So the acceleration is constant. What's that number? 9.8 meters per second squared. And the acceleration increases, or excuse me, the speed increases by 9.8 meters per second each second. So which one of these images below represents the position of a ball at equal time intervals as it falls freely from rest? So as it falls freely from rest, it's going faster and faster and faster. So each second, it's going farther and farther and farther. Which one represents that as the ball falls? It would be choice 2. Choice 1 would represent constant velocity. Choice 3 represents an object slowing down as it goes downward because it's going less and less distance. All right, and this would show an object slowing down then speeding up. 8 says an object is dropped from rest and falls freely 20 meters to the earth. What is the speed of the object, or when is the speed of the object 9.8 meters per second? Don't do any math, read 1a. So 1a tells us that an object's velocity changes by 9.8 meters per second every second. Okay, so it's constantly changing by that much each second. So when is the speed of the object 9.8 meters per second? Well, a couple things. We know it's changing, right? So it's not during the entire fall, okay? Not during the entire fall. And it's not when it falls 9.8 meters. So we're really just down to the entire first second or the end of the first second. So there's some different ways to think about this. When you first, like the millisecond after you release it, okay, that's when the first second begins. At that first millisecond, is it going 9.8 meters per second? No, right? Also, if it were traveling at 9.8 meters per second for the whole first second, that would be like it falls at 9.8 meters per second for a whole second, and then after 1 second, it jumps to 19.6 meters per second for the whole second. Then it jumps to 29.4 meters per second for the whole third second. So it's at the end of the first second. That's when it's going 9.8 meters per second. All right. So it's slowing down so it goes from 0 to 9.8 gradually over the course of the first second. So this one, number 9, says a ball is thrown vertically upward with an initial velocity of 29.4 meters per second. What is the maximum height reached by the ball? So here's my initial position. Initial. Ball is thrown upward. Here's my final position. All right. So if we look here, my initial velocity is 29.4 meters per second. Always make your initial velocity positive. Doesn't really look like we have a lot more information. We actually have a lot more information. Max height. At the max height, this is an important point, right? At the max height, final velocity equals 0. So we have another given there. Okay, we're looking for how high the ball goes, so that's D. All right, let me just fix that, or else that won't show up on the PDF. D equals unknown. Okay, and then A. What is our acceleration due to gravity? Well, we know it's 9.8 meters per second squared, but the question is it positive or negative? Remember, if the acceleration hurts the initial velocity, it's negative. If it helps it, it's positive. Look at the initial velocity. Is acceleration, is gravity helping it speed up, or is it slowing it down? Obviously, you know it's slowing it down, so we have to make this negative. All right, some people just like to memorize that. If the ball is thrown up, make the initial positive and make a negative. You can do that too. So to solve for this, you would do VF squared equals VI squared plus 2AD. All right, so VF is going to be 0 meters per second squared equals, let's see, the initial is 29.4 meters per second. That's squared plus 2. A is negative 9.8 meters per second squared. D is my unknown. Solve for D, and you should get D equals about 44.1 meters. All right, just be careful working through that algebra there. Now for the next one here, a ball is thrown straight downward with a speed of 0.5 meters per second from a height of 4 meters. What is the speed of the ball 0.7 seconds after it is hint? Again, it does not fall the full 4 meters. Okay, if it fell the full 4 meters, you could either use the 4 meters or the 0.7 seconds. You can't use both though. So this is actually information you do not want to use. Don't use the 4 meters. It's actually a little confusing. So let's draw a little picture here. This is my initial position. Ball is thrown downward with an initial velocity of 0.5 meters per second. Do I make that positive or negative? Always make your initial direction positive. All right. So the ball goes down to here. This is my final. All right. So what else do I have? Well, I know that the time that's elapsing is 0.7 seconds. And I know that my acceleration, let's see. So is my acceleration helping the initial velocity? Let's see, the initial velocity is going down. Acceleration, yeah, it's speeding it up, so I'm gonna make it positive. So some people like to think about, well, if a ball is dropped or if it's thrown downward, make the acceleration positive. Sure, you could do that. All right, and it's looking for V final. How fast is it going at the bottom? So VF equals VI plus AT. VF equals 0.5 meters per second, plus a, which is 9.8 meters per second squared, plus t, which is 0.7 seconds. So your final velocity comes out to be 7.4 meters per second. Now, what's the difference between speed and velocity here? Well, velocity needs a direction, so just make sure you emphasize that it is downward, all right? So there you go. There's class number 17. Let me know if you have any questions.